Welcome to the class of Advanced Stats and Econometrics. In today's lecture, we are going to discuss the remaining part of the factor analysis. In the last lecture, I have discussed stage 1, 2, and 3 of factor analysis. And in the stage 4, we need to derive factors and assessing overall fit. So, selecting the factor extraction method, common versus component analysis, determining the number of factors to represent the data. So extraction decisions, which method? Principal component analysis or common factor analysis. Second is how to rotate, orthogonal or oblique rotation. In orthogonal rotation, we maintain the 90-degree angle between the axis x and y axis. And in oblique, that condition is relaxed, so any angle is okay. Extraction method determines the types of variance carried into the factor matrix. So diagonal value, variance, total variance, commonality, common and specific, and error. So variance is extracted, variance not used. Principal components versus common. Two criteria. Objective of the factor analysis, amount of prior knowledge about the variance in the variables. Number of factors. There are four criteria. One is a priori criteria, in which we decide before seeing the data that we will have these many factors. Latent truth criteria is eigenvalue. Based on the eigenvalue, if eigenvalue is greater than 1, only those factors will be selected. Percentage of variance, we decide that we will stop when we are able to explain a certain minimum percentage of variance, say 70% or 80%, whatever we have decided. Once we reach that, we will stop adding factors. Scree test criteria is looking at the point of inflection or where the curvature is changing. We plot eigenvalue with number of factors. So eigenvalue plot for Scree test criteria, you see that on x-axis we have latent truth or eigenvalue, on x-axis we have factor number. So first is having highest, second is after that third, and fourth and fifth. So if on the basis of latent truth criteria, if we look at eigenvalue greater than 1, then we will be able to select 8 factor, because for 9 the value is less than 1. For Scree test criteria, you see it is 10, because after 10 there is a gradual decrease in the value of the eigenvalue. Choosing factor models and number of factors. Although both component and common factor analysis models yield similar result in common result setting, 30 or more variable or commonality of 0.60 for most variables. The component analysis model is most appropriate when data reduction is paramount. The common factor model is best in well-specified theoretical application. Any decision on number of factors to be retained should be based on several considerations. Use of several stopping criteria to determine the initial number of factors to retain. Factors with eigenvalue greater than 1. A predetermined number of factors based on research objectives and or prior research. Enough factors to meet a specified percentage of variance explained, usually 60% or higher. Factors shown by the Scree test to have substantial amount of common variance factors before inflection point. More factors when there is heterogeneity among sample subgroups. Consideration of several alternative solutions, one more and one less factors than the initial solution to ensure the best structure is identified. Process of factor interpretation. Estimate the factor matrix, factor rotation, factor interpretation, de-specification of factor model if needed. It may involve deletion of variables from analysis, desire to use a different rotational approach, need to extract a different number of factors, desire to change method of extraction. Rotation of factor. Factor rotation. The reference axis of the factors are turned about the origin until some other position has been reached. Since unrotated factor solutions extract factor based on how much variance they account for, with each subsequent factor accounting for less variance. The ultimate effect of rotating the factor matrix is to redistribute the variance from earlier factors to later ones to achieve a simpler, theoretically more meaningful factor patterns. Two rotational approaches. One is orthogonal, in which axes are maintained at 90 degree. Another is oblique, axes are not maintained at 90 degree. So you can see that for orthogonal factor rotation, we begin with unrotated factor 1 and unrotated factor 2, x and y axis. Then we rotate both uh, axes clockwise with the same angle. So rotated factor 1 and rotated factor 2 maintains the 90 degree angle. And in this you can see, after rotation, variable 2 and 4 are mostly captured by factor 2, and variable 3, 4, sorry, variable 1 and 2 are captured through factor 2, and variable 3, 4, 5 are mainly captured through factor 1. So in the case of oblique rotation, we don't need to maintain the 90 degree. So angle of rotation can be different for x and y axis. Orthogonal rotation matrix. So there are three ways of doing orthogonal rotation matrix. One is quatrimax, another is varimax, and third is equimax. So quatrimax is going to simplify the row, varimax is going to simplify the columns, and equimax is a combination of both. Choosing factor rotation methods. Orthogonal rotation methods are most widely used rotation methods, and they are preferred method when the research goal is data reduction to either a smaller number of variable or a set of uncorrelated measures for subsequent use in other multivariate techniques. Oblique rotation methods are used. They are best suited to the goal of obtaining several theoretically meaningful factors or construct, because realistically very few constructs in the real world are uncorrelated. Which factor loadings are significant? Customary criteria, practical significance. Uh, so we have sample size and statistical significance. Number of factors you add or delete, or you increase the number of variables, remain equal to the number of factors or so. Guidelines for identifying significant factor loading based on sample size. Factor loading, if factor loading is high, then your sample size needed for significance will be low. So if you increase factor loading, if the factor loading is high, then sample size needed for significance, you can see, as the factor loading increases from 0.30 till 0.75, the sample size needed for significance decreases from 350 to 50. And significance here is based on 5% or 0.05 level of significance, a power level of 0.80, and standard error assumed to be twice those of conventional correlation coefficients. Assessing factor loading. While factor loading of plus minus 0.3 to plus minus 0.4 are minimally acceptable, values greater than 0.5 are considered necessary for practical significance. To be considered significant, a smaller loading is needed given either a larger sample size or a larger number of variables being analyzed. A larger loading is needed given a factor solution with a larger number of factors, especially in evaluating the loading on later factors. Statistical tests of significance for factor loadings are generally very conservative and should be considered only as starting point needed for including a variable for further consideration. Interpreting the factors, that is part of stage 5. Selecting the factors, extraction method, common versus component analysis, determining the number of factors to represent the data. Interpreting a factor matrix. Examine the factor matrix of loading. Identify the highest loading across all factors for each variable. Assess communality of the variable. Label the factors. Interpreting the factors. An optimal structure exists when all variables have high loading only on single factor. Variables that load highly on two or more factors are usually deleted unless theoretically justified or the objective is strictly data reduction. Variables should generally have a communality of greater than 0.50 to be retained in the analysis. Re-specification of a factor analysis can include options such as deleting a variable, changing rotation method, and or increasing or decreasing the number of factors. Stage 6 is validation of factor analysis. So confirmatory perspective, assessing factor structure stability, detecting influential observations. Stage 7 is additional use of factor analysis results, selecting surrogate variable, creating summated scales, computing factor scores. Summated scale. A summated scale is only as good as the items used to represent this construct. While it may pass all empirical tests, it is useless without theoretical justification. Never create a summated scale without first assessing its unidimensionality with exploratory or confirmatory factor analysis. Once a scale is deemed unidimensional, its reliability score, as measured by Cronbach's alpha, should exceed a threshold of 0.70. Although a 0.60 level can be used in exploratory research, the threshold should be raised as the number of items increases, especially the number of items approaches 10 or more. With reliability established, validity should be assessed in terms of convergent validity scales correlate with others like scale. Discriminant validity scale is sufficiently different from other related scale, and nomological validity. That means scale predicts the theory as theoretically suggested. Representing factor analysis in other analysis. The single surrogate variable. Advantage: simple to administer and interpret. The disadvantage: first one is it doesn't represent all facets of the factor. Second is it is prone to measurement errors. Factor scores. Advantages are three. First is it represents all variable loading on the factor. Second is best method for complete data reduction. Third is they are by default orthogonal and can avoid complication caused by multicollinearity. Disadvantages are interpretation more difficult since all variable contribute through loading. Second is difficult to replicate across studies. Summated scale. So advantages are compromise between surrogate variable and factor score option. Second is it reduces measurement error. Third, it represents multiple facets of a concept. Fourth is it is easily replicated across studies. Disadvantages: it includes only the variable that loads highly on the factor and exclude those having little or marginal impact. And second disadvantage is it is not necessarily orthogonal. Third is it requires extensive analysis of reliability and validity issues. So here we can see rotated component matrix, reduced set of HBAT perception variables. So we have component 1, 2, 3, 4 and communality, and you have variables x9, x18, x16 till x13. And variables are complaint resolution, delivery speed, order and billing, sales image, e-commerce activity, advertising, technical support, warranty and claims, product quality, and competitive pricing. So sum of squares and percentage of trace is given, and the extraction method is principal component analysis. Rotation method is varimax. Scree test for HBAT component analysis. As you can see here, we have eigenvalues and factors. So we are going to include on the basis of factors having eigenvalue greater than 1. There are 4 factors. Fifth one is having eigenvalue less than 1. So it is not going to get selected. Factor analysis learning checkpoint. What are the major uses of factor analysis? What is the difference between component analysis and common factor analysis? Age rotation of factor necessary? How do you decide how many factors to extract? What is significant factor loading? How and why do you name a factor? Should you use factor scores or summated rating in follow-up analysis? And the reference for all this is a book titled Multivariate Data Analysis, 8th edition. Publisher is Cengage Learning. Authors are Hare, Babin, Anderson, and Black. Thanks for today's class. That's it.